This is a video from section 9.3, the directions say to solve the differential equation. We're going to go ahead and start with example 1. Suppose I have dy dx equals 3x squared y squared. So this is a separable differential equation, so I could write it as follows. 1 over y squared dy is equal to 3x squared dx. Now what I want to do is I want to integrate both sides. So the integral of 1 over y squared dy is the same as the integral of 3x squared dx. So let's rewrite that over here. The integral of 1 over y squared dy is the same as the integral of 3x squared dx. So negative 1 over y, that's the function whose derivative is 1 over y squared. This is equal to x cubed plus c. Okay? So if we solve for y, we get y is negative 1 divided by x cubed plus c. All right? So therefore, the answer is the following. Y equals negative 1 over x cubed plus c. But by the way, if y equals 0, the derivative of 0 is 0, and so I claim that's also a solution to the differential equation as well. So we would have to write y equals negative 1 over x cubed plus c, and additionally y equals 0. And that's the answer to example 1. Let's take a look at example 2. Suppose we had dy dx is x times the square root of y. So again, this is a separable differential equation. So 1 over the square root of y dy is equal to x dx. And when I'm doing this, I'm writing the differential equation in differential form. And that's going to enable me to integrate both sides here. So I take the integral of 1 over square root of y dy. This is the same as the integral of x dx. So again, I want the function whose derivative is 1 over square root of y. And that's going to be 2 times the square root of y. That's on the left side. On the right side, I want the function whose derivative is x. And that's going to be 1/2 x squared. And then I just have to add that constant of integration, c. Now, let's divide both sides by 2. So square root of y is the same as 1/4 x squared, right, plus 1/2 c. So what I'm going to do is I'm going to let k equal 1/2 c. Just call it a different constant, okay? So square root of y is the same as 1/4 x squared plus k. Now, so if we square both sides, we get y is 1/4 x squared plus k to the second power. So the answer to this one is y equals 1/4 x squared plus k to the second. And also, again, if y equals 0, the derivative of 0 is 0. And so that's also a solution to this particular differential equation. So y equals 0 does indeed work. Example 3. suppose we had xy times dy dx equals x squared plus 1. So I'm going to, again, split this up, and we're going to write this as y dy on the left side. And on the right side, we get x squared plus 1 divided by x dx. So y dy is equal to x plus 1 over x dx. So on the right-hand side, I just split off the fraction. That allows me to integrate both sides. So y dy, the integral of that is the same as the integral of x plus 1 over x dx. So 1/2 y squared, that's the function whose derivative is y. This is the same as 1/2 x squared plus natural log of the absolute value of x plus c, right? Now, what I want to do is I want to multiply through by 2. So y squared is x squared plus 2 times the natural log of the absolute value of x plus k, where k equals 2c. Solving for y, I get plus or minus the square root of x squared plus 2 times the natural log of x plus k. And this time, on this example, y equals 0 does not work as a solution to this differential equation. Okay? Let's take a look at example 4. Suppose I had e to the y minus 1 dy dx is 2 plus cosine x. So we're going to write this differential equation as e to the y minus 1 dy is the same as 2 plus cosine x dx. That allows me to integrate both sides. So e to the y minus 1 dy, the integral of that is the same as the integral of 2 plus cosine x dx. So I get e to the y minus y on the left side. On the right side, I get 2x plus, so notice the function whose derivative is 2 is 2x. The function whose derivative is cosine x is sine x. So I get 2x plus sine x plus some constant c. And this is one situation where we're not able to solve for y in terms of x. So it would be pretty acceptable to leave the answer in this form. Okay? That's example 4. Let's take a look at example 5. Suppose I had dp dt is t squared p minus p plus t squared minus 1. So dp dt, I'm going to factor by grouping. So in the first two terms, I factor out a p, and I get t squared minus 1. In the second two terms, I factor out a 1, and then I get t squared minus 1. So dp dt is t squared minus 1 times p plus 1, right? And this is separable. It doesn't look like it in the beginning, right? But we can separate this. So 1 over p plus 1 dp is going to be the same as t squared minus 1 dt, right? So we write it in differential form, and then we integrate from here. So the integral of 1 over p plus 1 dp is the same as the integral of t squared minus 1 dt. So natural log of the absolute value of p plus 1 is 1/3 t cubed minus t plus c. Okay? Now, what we can do is the following. So the absolute value of p plus 1 is e to the 1/3 t cubed minus t plus c. Okay? Now, this says the absolute value of p plus 1 is ae to the 1/3 t cubed minus t, where a equals e to the c. So let's write that over here. The absolute value of p plus 1 is ae to the 1/3 t cubed minus t. So p plus 1 is plus or minus ae to the 1/3 t cubed minus t. So if I solve for p, I get -1 plus or minus a e to the 1/3 t cubed minus t. Another way you can write this is you can say p is equal to -1 plus k e to the 1/3 t cubed minus t. This would be okay, but you would just have to specify that k is plus or minus a, essentially. That's what I would do. But it's, again, one of those things where you want to double check with your instructor on how your instructor wants you to leave your answer. But I will tell you the hardest part, I think, is solving for p in terms of t. Okay? That's how you do example. This is, I believe, example 5. Yeah. Let's do one more example for this video. Let's take a look at example 6. So we'll do this one. Suppose I had dy dx plus x e to the y equals 0. So dy dx is equal to -x e to the y. So 1 over e to the y dy is the same as -x dx. And so e to the -y dy is the same as -x dx. So this allows me to integrate both sides. So the integral of e to the -y dy is the same as the integral of -x dx. So -e to the -y, right? That's the function whose derivative is e to the -y. And you could use the chain rule to check that, right? Now, on the other side, the function whose derivative is negative x is negative 1/2 x squared. And remember, we have to add our constant of integration. Okay? So e to the negative y is the same as 1/2 x squared plus, we'll call it k, where k equals negative c. So negative y is the same as natural log of 1/2 x squared plus k. So I essentially took the natural log of both sides. And in fact, e to the negative y is positive, and so that means under appropriate values of x, right, and of course k, that right side has to be positive as well, so we don't need absolute values. So technically we could do this. And so y is negative natural log of 1/2 x squared plus k. And that will conclude this video for section 9.3, where we solved the given differential equation. And they were all separable differential equations. Okay, thank you.